Hi everyone, I would like to begin by thanking the organizers for giving me this opportunity, and to everyone listening, thank you for your time. Before I get into the details of my presentation, a quick note: you can submit your questions for me throughout the presentation, and at the end of the presentation, I will try to answer as many of them as I possibly can. If I don't get to your question, or if you think of something later on, to drop me an email. I look forward to your feedback. Today, I will be presenting Phen-Gen, a computational method that we have recently developed at Genome Institute of Singapore to analyze rare disorders. A key strength of Phen-Gen is that it integrates phenotype or the patient's symptoms along with the genotype, which is patient sequencing data, in implicating what is the most likely causal gene for this person's condition. Another strength of Phen-Gen is that it works both with coding variants and it also looks at genomic variants. We did what every self-respecting computational biologist would do. We ran it over lots and lots and lots of simulations, and Phen-Gen tends to outperform competition by about 13 to 58%. To make it available as a community tool, we have implemented it as an online server. The link is shown at the bottom, phengen.com or phengen.org. So you can go to this website and upload your VCF file, patient symptoms, and a pedigree file, and get the results back in about 15 to 20 minutes. The source code for Phen-Gen is available, and it is released under the GNU license. So people can download it and modify it according to their needs, or run it on their own servers. Phen-Gen was recently published in Nature Methods, and I believe it is still an online advanced publication. Whenever I talk about rare disorders, I always like to include a picture of Nick Walker, shown on the right top here, because Nick was one of the first patients whose disease was diagnosed using next-generation sequencing, and this diagnosis helped his doctors come up with his treatment, which improved the quality of his life, which is the holy grail of any such analysis. Before I get into the details of Phen-Gen, a quick word on what is the existing paradigm to analyze rare disorders. It all starts with a patient who's suffering from a list of symptoms and reports these symptoms to the doctor. The doctor prioritizes these symptoms according to their domain knowledge and finds out and predicts what is the most likely diagnosis for this patient. If he suspects a rare disorder with a genetic cause, he may decide to go for sequencing. A key point of emphasis that I would like to make here is that once the geneticist comes into the picture, the main focus quite often is just the fact that this is a rare disorder. So we put the patient's symptoms on the back burner for now and focus only on the fact that this is a rare disorder. So the genetic cause is likely going to be a rare, highly deleterious mutation. Once the sequencing comes in, everyone has their favorite tools. But the main objective of this part of the analysis is to shortlist and get to a small list of genes which are most likely harbor a bad mutation and hence are the cause of this person's condition. Once this shortlist has been established, then you go back and look at the patient's condition and try to figure out how can we link these conditions to one of the genes in our list. What is the drawback of this approach? One obvious drawback is that you have a list of genes and you have a list of symptoms and you are trying to match them, and you may end up connecting them through 6 degrees of separation. Another drawback is that quite often when you use computational tools like SIFT and Polyphen, people use hard cutoffs. So if SIFT says that the mutation is definitely damaging, we are going to include it in our analysis. But if it's possibly damaging, we might check it out. And these possibly damaging mutations could be a potential causes of the patient's condition. It's very easy to criticize. It's more fun to come up with a solution, which is what we are aiming to do in Phen-Gen. In Phen-Gen, we improve this analysis by first using the patient's symptoms to define a prior probability of involvement of each gene with this set of symptoms. Second, we quantify commonly used deleteriousness predictors. So for example, if SIFT assigns a particular score to a mutation and Polyphen assigns a particular posterior probability, what is the probability of this particular mutation being damaging? And then we combine these two predictions in a unifying framework. To look at the big picture, we follow 2 independent paths to disease gene implication. The first part, shown on the left here, is the phenotypic part, where we are looking at the patient's symptoms and trying to estimate the probability of involvement of each gene. The second part is the genotypic part, shown on the right here, where we are looking purely at the patient's sequencing data. So how we use the phenotypic information? In the first step, we use the patient's symptoms and match them to a list of known disorders using Phenomizer. So basically, we are trying to find the probability of involvement of these genes, which have been implicated for similar disorders. We take these probabilities and use a random walk with restart on a gene interaction network to assign probabilities to other genes which have a similar functional role. At the end of this stage, we have assigned a score to each gene, shown in red on the left side, shown in red on the left side. What is the probability of involvement of each gene based purely on the disease symptoms? In parallel, we look at the person's sequencing data and try to assign a probability of deleteriousness to each variant. We pool these probabilities within genes and assign scores to each gene. The next obvious step is to combine these two probabilities based on phenotype and genotype in a unifying framework and use a Bayesian approach. I will talk about the variant predictors in the next few slides, but before I get to that, a big overall picture. I'm not going to go into all the details of different components, but I like to include this slide in case people have questions of how different components integrate with respect to each other. And in that case, I can go back to this slide and explain everything in detail. But a few things that I would like you to focus on here on the top, when I talked about the gene interaction network, this is a probabilistic gene interaction network which was constructed in-house by integrating 7 different data sources. The second part that I would like you to focus on are that we have 2 different predictors, one for coding mutations and one for all genomic mutations. And I will be talking about these 2 predictors in the next slide. For coding mutations, we divide them into 3 categories: non-synonymous mutations, non-single splice site mutations, and indels. When I said coding, we use a union of 4 different databases which are consensus, RevSeq, UCSC, and Ensemble to define all coding transcripts. For non-synonymous mutations, we use SIFT and polyphen, and we combine the predictions of these 2 methods. For splice site mutations and nonsense mutations, we use the aforementioned 4 databases to define these loci. For indels, we further subdivide them into 2 categories, as either frameshift or non-frameshift. If they are non-frameshift, we also look at the importance of that site. All these predictors have been quantified using human gene mutation database, disease causal variants as a positive set, and common mutations in DBSNP as a neutral set. Further, for non-synonymous mutations, we use human chip gorilla alignment to define a set of benign mutations. So these are mutations in which the human reference sequence carries the alternate allele, which is different from chimp and gorilla sequences. If you cannot see the picture on the right, this is an illustration from George Orwell's book, The Animal Farm, where he says that all animals are created equal, but some animals are more equal than others. If you recall last year, the big ENCODE paper said that most of the genome was functional. The aim of our predictors is to find loci which are more functional than others. To put it in more scientifically precise terms, we are trying to find loci where mutations are more likely to be damaging. And we look at conservation, mutative functionality, and whether the mutation is near a gene or not to make this prediction. In particular, we use GERB and PILOB to define conservation of a locus. We use the aforementioned 4 databases to define gene transcripts and whether the mutation is near one of those or not. And we use 2 annotations from ENCODE project, one for the transcription factor binding sites, and the second one for DNA hypersensitive sites. We also evaluated Gumby non-coding RNA from GenPro, GC content, and microRNA databases. But in general, overall, the 5 categories on the left showed better performance. So how well do they perform? Since there are 5 categories, so there are 2 raised to the power 5, which is 32 possibilities of annotation combinations. If you focus on the bar on the extreme right, at the bottom it says all, and this is showing if a mutation is at a locus which is considered conserved by both GERB and PILOB, it is near a gene, and it is at a predicted transcription factor binding sites and in my open chromatin region, a mutation there has a probability of 0.83 to be damaging. If you focus on the extreme left, at the bottom where it says none, if a mutation is not considered conserved by curve or phylo P, it's far away from any known gene, it is not considered a transcription factor binding site or a DNase hypersensitive site, the mutation there is very likely to be benign. The probability is near zero that it's damaging. So how well do these predictors perform? Here I'm showing you the performance of these predictors using human gene mutation database disease causal variants. On the top three panels, I show the prediction performance of coding predictors, and the bottom one is for the genomic predictor. As you can see, the top three panels are mostly squished towards the right, which shows that the coding predictors tend to do well. Just like other methods, we tend to perform much better for coding variants. It's much more challenging to evaluate the deleterious role of non-coding mutation, and that's why the panel at the bottom, the mutation is spread a little bit more along the x-axis. Moving on to next slide. So before I had shown you the performance of the variant predictors individually. Now, how does Phen-Gen perform overall? In order to evaluate that, we did a lot of simulations. And what we did in the simulations was that we picked a healthy person from the 1000 Genomes Project, add a damaging mutation from human gene mutation database into this healthy genome, define the genotype, download the patient's symptoms for this particular disorder from OMIM to define the phenotype, and then feed both this phenotype and genotype to Phen-Gen and analyze how often is Phen-Gen able to identify the disease causal gene as top rank gene, top 5 gene, and top 10 genes. And here are the results. Generally, it's easier to evaluate the performance or to predict for recessive disorders, and it's a little more challenging to predict for dominant disorders. This is what we see in the top row here too. So in 81% of the dominant simulation, Phen-Gen is able to correctly identify the disease causal gene as top rank gene. For recessive, the performance is much better. In 96% of the simulations, Phen-Gen was able to correctly identify the disease causal gene if inheritance pattern was recessive. We split the performance based on genotype only and based on phenotype only as well. Also, if the disease gene link is known to Phen-Gen, then it tends to perform better, which is shown in the last two rows. How do these numbers compare to competitors? Here, there's a lot going on, so I will go into a little more detail for this particular slide. The top two panels, we compare Phen-Gen with VAST and ecstasy. If you focus on the first column, which says top gene, here I'm showing you Phen-Gen's performance shown by PG and Tiffany. And Phen-Gen's bar is split into two colors. The dark blue color shows how often is Phen-Gen able to identify the disease causal gene as top rank gene based purely on the genotypic prediction, and the added advantage of integrating the phenotype. The second bar, B, stands for VAST. VAST does not use sufficient symptoms, and it on average assigns multiple genes the same top rank. So in order to compare it, to make it a fair comparison, what we do is that we take that if VAST assigns the causal gene, let's say rank 1, and it assigns the same rank to 5 different genes, to 4 more genes, then we would assign it best, which would be 1, average, which would be 3, and worst, which would be 5 of these genes. And the VAST bar is split into these 3 colors. The third bar is ecstasy, shown in red and pink here. Ecstasy was recently published, and it integrates the patient's symptoms in its prediction. In its publication, it was evaluated for all mutations and also restricting it to rare mutations only. And the two components of the ecstasy bar shows its performance under these two scenarios. While Phen-Gen was under review, Fever was published by the authors of VAST. So what Fever does is that it takes a genotypic predictor and reprioritizes the variants based on the disease symptoms. Unfortunately, Fever was not available as a downloadable bundle. It was only available as an online package, so we used a subset of simulations to compare Phen-Gen with Fever. We used 100 simulations, 50 for dominant and 50 for recessive. And here at the bottom two panels, I'm showing you our comparison with Fever plus VAST. In general, Phen-Gen outperforms competition by 13 to 58%. And if you take the average of dominant and recessive simulations, it is able to identify the disease causal gene in 88% of the simulations. We all love simulations. Simulations are great, but they are not a substitute for real data sets. And a big challenge when you're working with rare disorders is to get your access to these data sets. And we were lucky that the authors of a recently published paper in New England Journal of Medicine, which analyzed 100 intellectual disability patients, were kind enough to share the data with us. Here I'm showing you the performance of Phen-Gen for 11 of these 100 patients. Why did we focus on 11? Because one of the challenges of this real data set was that in the original paper, they were focusing on de novo mutations. So they were very liberal in their variant calls. Unfortunately, this led to the initial variant calls to be a little noisy. We focused on only 11 families in which the disease causal variant was inherited, and it was called in the correct inheritance pattern within the family. I'm showing you Phen-Gen's performance in each of these families. In 8 of 11 families, the top ranked gene by Phen-Gen was also considered disease causal in the original paper. And in all cases, all disease causal variants implicated in that paper were within top 5 ranked by Phen-Gen. I've highlighted a particular family, 3 or 4, for which they have implicated 3 potential candidate genes, and these 3 genes are assigned 1, 2, and 3rd rank by Phen-Gen as well. I would like to finish my presentation by acknowledging my co-authors and to a lot of people for their support for this paper. And I would like to thank you all for your time, and I look forward to your questions. I don't see a lot of questions, but if you have any questions later on, do drop me an email, and I look forward to your feedback. Let me see if there are any questions.